So what we might do is simply model a dz as a y times a square root of delta t. In other words, since the standard deviation of dz is the square root of dt, why not separate the normality part from the standard deviation part? So here y is standard normal. Y is now, no matter what dt is, we can just generate standard normal y's and use them to generate dz's. And then we control the size of the interval by the multiplier square root of dt instead of generating normal variables that are different. We're going to generate yt, the same normal variables, standard normals, and we'll fix the standard deviation with the multiplier square root delta dt or square root delta t. We can also generate yt as we did earlier in the binomial lattice, where we let the yt be the plus or minus 1. In other words, the simple random walk. Notice that a yt binomial that takes on values plus and minus 1 has a mean of 0 and a variance of 1. So it has the same two first moments as the standard normal, and so of course it's quite crude as a probability distribution compared to the normal, but it has the same two first moments, and we know that since we're going to be summing y values, if we sum binomials, we're going to get closer and closer to the normal that we're interested in. So this is a very advanced topic that is not really addressed in this book, but it turns out that there is an integration theory which allows you to go from the process dz and produce, by adding it up, by taking a limit of the sums, you can actually produce the value of z. This is not an integral that you might be familiar with. It certainly cannot be defined as the Riemann integral of calculus, nor even the Lebesgue integral of real analysis. Ito introduced a methodology for defining this integral, which is somewhat complex, but related to the tools of real analysis, and we don't need it for our purposes in this test, but the chapter does identify that there is an integration theory for which a formula that from a calculus perspective looks very natural. It looks familiar and it looks natural, and I'm only pointing out to say that this integral needs to be defined in a completely different way, even though notationally it has that familiar look of a formula from calculus. It's called a stochastic integral, and the process zt is sometimes called a diffusion process. So Brownian motion, the paths that one generates with these z's, the zt paths, have two important properties that I want to discuss next. One is called infinite variation, one is called infinite crossing. So what each of these is going to, I think, convince you of is that Brownian motion, this zt function, and it's really an infinite collection of paths, is a very exotic creature, which goes back to my earlier point that it by no means is obvious that such a creature exists. And so let's now investigate some properties that we can easily get comfortable are true, and they're quite, in a sense, mysterious. First one has to do with a notion called quadratic variation. And the notion of quadratic variation is we take an interval of time, 0t, and we break it up into, as usual, n periods. And then you can see in this summation, we look at the value of z at the beginning and the end of every subperiod. We just look at the beginning and the end, so the first term of this sum would be a zh minus z0. The next one would be z2h minus zh, and so forth. But before we sum it up, we square each value. Each difference of each change in z, we square. Now remember, each change in z's is normally distributed. Each one of the terms in this sum, each one of these delta z's, has a normal distribution, mean 0, variance h. And now we're going to square those delta z's and add them up. And the question is, what happens when the number of subintervals grows without bound? What happens when h goes to 0? This quadratic variation can also be defined more generally where the subintervals are not uniform, but we don't need to consider that. So we'll consider the simpler case where the subintervals are uniformly defined.